My question for you in class is going to be this one right here. Can you make an easy comparison between these two triangles? So some people might say, well, the green side's the same as the green one down here. That's a good comparison. Blue side here's, or purple side, whatever color that is on your screen, is congruent to the purple side down here. And I don't think I can make that not happen, right? I can grab F here, I could grab H down here, and the purple sides always stay 3.3. How about the green sides? Can we make the green side shorter? No, that just moves the triangle, right? There's oh. I didn't know I could do that. Okay, so don't mess with point A. I want those two to stay, the greens to stay the same and the purples to stay the same. So shoot, I should have fixed A somehow. All right, anyways, so that's an easy comparison, right? How about the red dashed segments over there? Can you make a conclusion about those red dashed segments? Well, let's just leave it like that for a second. If I had 29.3 here and 72.2 there, which one would be longer, or would they be the same length? I hope your brain's going, come on, Nelson. This one over here is shorter than this one over here because the angle here is smaller than the angle over there. We could make it more obvious, right? Make the angle really small, make this angle really large, and you can see, whoa, those are way different. If it still doesn't seem right to you, go down to the measure tool and click on distance. Okay, this thing pops up here. It says select 2 points, a segment, polygon, or circle. And so if I come over here and I select that segment right there, so I clicked on distance or length, right? And I click on the segment, it'll put 1.3 there, and it'll put 4 over here. You can see this one's way bigger than this segment, this red dash segment. So that's called the hinge theorem. If you have two sides in a triangle congruent to two sides in another triangle, and what's called the included angle, it's the interior angle of the triangle that's between the two sides that you know. That's why they call it included. It's between the two sides. It's the interior angle that's between the two sides that you know. That's the included angle, okay? So if the included angles are not equal to each other, well, then the side that's going to be bigger is across from the bigger angle. Now, you might say, I could make both of them say like 2 and the angles aren't equal. That's just because GeoGebra is rounding, so this one's slightly different. If we change the preferences to go out to like the thousandths place or something, we would see this one is longer than this one over here because this angle is bigger than that angle. So that's the benefit of understanding the hinge theorem, is that if you saw a situation like this and the computer claims they're both 2, this one's slightly longer than that one, right? So that's the comparison that we're trying to focus on. If this angle up here is bigger than that angle down there, then this side is longer than that one up there or down there. So let's go back to our notes and let's write that down. All right, so the way I had the drawing set here was that this angle here is smaller than this angle down here. So this side right here is smaller than this side down here. This one's larger. Now, if we're trying to look fancy and we're writing an inequality down, I'd put down something like this. Segment EF, like with nothing over the top. That means the distance, the length of segment EF is less than the segment GH's measurement. So the length of GH with nothing over the top means the distance between G and H. So this is the conclusion that we can come up with fairly easily. I hope you agree with me on that. Now, what I'm going to do is I'm going to walk us through this word problem. And then in class, we're going to break out and we're going to work on the whiteboards together with partners. But it says something like this: 2 families set sail from the same dock. So I'm going to put a boat right down here. And I'm not going to make a copy of this boat. I guess I could, but I'm just going to reuse the boat. All right. So the first family is the Winds, and they sail 3.5 nautical miles north. Okay, so let's just do that real quick. So this boat looks to me like it's going to go to the east, right? So I'm going to rotate the boat to make it go to the north. All right, so let's see right there. Now the boat's going straight north. And oh, by the way, this is going to be our common dock right here, right at the center of our axes. the origin, right? And so if I grab the boat, oh geez, why is it not letting me choose the boat? Hold on one second here. There we go. If I grab the boat and I put it at the origin and I go due north for 3.5 miles, and then I turn 85 degrees east of north. So let's think about that for a second. 85 degrees east of north. Okay, so I'm going to try to make it look like I'm going 85. Well, 90 degrees would be like due east, right? So I'm going to go just a tiny bit less. I'm going to say that's 85 degrees. Now the boat goes 2 miles. Okay, so here we go. 2 miles in that direction, right? So it ends up over here somewhere. All right, well, I'm going to draw that to kind of record where the boat went. It went due north for 3 miles. So I'm going to say that's 3. And then it went at like an angle kind of like this. And I'm going to say that's 2 miles right there. So let's check them off. Oh, shoot, that needs to be 3.5. See, that's why I kind of want to go back and check it off. 3.5 and 2 miles, right? Now let me go get the boat again, and we'll put it back at the proverbial origin. And let's rotate it back so it's going just straight. Oh, now it's kind of weird. All right, so let's pretend like there's our boat right there. Okay, so if it went like that, it would go east, right? But this family, the Griffins, they sail 3.5 nautical miles due south. So let's rotate this baby 90 degrees down, and we're going to make it go due south. So right down there, right? Okay, let's move our little drawing up here so we can see it. So, okay, let's record where it just went. It went 3.5 due south. Here we go, 3.5 due south. Boom. Hey, look at that, 3.5, 3.5. Now watch, we're going to turn the sailboat. And we want to turn the sailboat 95 degrees east of south. So right now it's going east. This way is, right now it's going south. This way is east. And we want to rotate the boat 95 degrees. So it turns 90 degrees and then it turns just a little bit more. All right. And it's going to go 95 degrees like that direction for 2 miles. Okay. So let's record that part. So here we go. 2 miles, kind of like in that direction. All right, so 2 miles. Now let's get rid of the boat here so it's not in our way. And let's try to kind of center this up so we can see what's going on. Which family is further from the place that we started from the port? I think common sense would say this family right here is closer because they kind of angled back toward, not completely toward it, but like in an angle that's not getting us further away from the dock, as opposed to this family that turned like that and was going further away from the dock, right? This one's not getting closer to the dock, but it's just like it's at an angle that's not completely away from the dock, right? So this angle that your brain, and I hope your brain's looking at it like right in here, this is called the included angle. Well, if the rotation that this family did was 95 degrees, right? Wouldn't that leave 85 degrees right in there? And if this family rotated 85 degrees this way, I hope you would agree that this angle right in here has to be 90 degrees. So it's kind of weird, but the interior angles in this situation kind of get flopped, don't they? That's just a matter of it adding up to 180 degrees, right? 85 and 95 make 180, I think. 85 and 95 make 180, yeah. But I had to find the included angles to really show the hinge theorem, right? And so let's go to a different color here. What color was it on our GeoGebra sketch? Wasn't it like a red dash line? Yeah. So shoot, I'm already using red. I guess I'll continue with red. I'll make it red dashed. Okay, this distance here is longer than this distance right over here. This is shorter. So that is hopefully answering their question. Let's go back over here and just reread it one more time. It says, at this point, which boat is farther from the dock? Explain your reasoning. Well, I think this was the Wynn family right up here. So the Wynns are further away from the dock than the Griffins. All right. Hey, I hope I made that clear. Like I said, in class, we are going to work on problem number 2. We're going to do problem number 1 with our partners at the whiteboard. and hopefully kind of make some sense of this. So we'll practice that whole movement idea of an object away from the origin or something like that. And if you want to try this one on your own, I'll make a second video for you, and we'll walk through problem number 1. All right. Thanks for watching my video.